Electromagnetic induction. The discovery that an electric current in a wire produced magnetism was a turning point in physics, and the technology that followed. The question arose as to whether magnetism could produce electric current in a wire. In 1831, two physicists, Michael Faraday in England and Joseph Henry in the United States, independently discovered that the answer is yes. Until their discovery, the only current-producing devices were voltaic cells, which produced small currents by dissolving expensive metals and acids. These were the forerunners of our present-day batteries. The discovery of Faraday and Henry provided a major alternative to these crude devices. The discovery was to change the world by making electricity so commonplace that it would power industries by day and light up cities by night. Here's a picture of a nuclear power plant turbine room. Chapter 37.1 Electromagnetic induction. Faraday and Henry both discovered that electric current would be produced in a wire by simply moving a magnet in or out of a wire coil. No battery or other voltage source was needed, only the motion of a magnet in a coil or in a single wire loop. They discovered that voltage was induced by the relative motion of a wire with respect to a magnetic field. The production of voltage depends only on the relative motion of the conductor with respect to the magnetic field. Voltage is induced whether the magnetic field or magnet moves past a stationary conductor, or the conductor moves through a stationary magnetic field. The results are the same for the same relative motion. The amount of voltage induced depends on how quickly the magnetic field lines are traversed by the wire. Very slow motion produces hardly any voltage at all. Quick motion induces a greater voltage. When the magnet is plunged into the coil, voltage is induced in the coil and charges the coil are set in motion. Figure 37.2. Voltage is induced in the wire loop whether the magnetic field moves past the wire or the wire moves through the magnetic field. The greater the number of loops of the wire that move into a magnetic field, the greater the induced voltage and the greater the current in the wire. Pushing a magnet into twice as many loops will induce twice as much voltage. Pushing it into 10 times as many loops will induce 10 times as much voltage, and so on. Figure 37.3. When a magnet is plunged into a coil of twice as many loops as another, twice as much voltage is induced. If the magnet is plunged into a coil with 3 times as many loops, then 3 times as much voltage is induced. Does it seem that we are getting something energy for nothing by simply increasing the number of loops in a coil wire? We don't. The law of energy conservation is not just a law of mechanics, it is a law of nature. It applies everywhere, and the experiments shown in figure 37.3 and 37.4. The force you can exert on the magnetic multiplied by the distance that you move the